Inside a waveguide, light can exist in multiple modes or paths. Light does not always travel in a single straight path. In optical waveguides, light follows specific patterns called modes, and it is known as the coupling of waves and modes. So, what is modes? Inside a waveguide, light can exist in multiple modes or paths. Each mode carries part of the light energy. When the waveguide is disturbed, such as by a nearby structure or a change in geometry, the light can move from one mode to another. This process is known as mode coupling. It also simplifies the analysis. Moving on to the rules for an efficient CMT. Firstly is the phase matching. For efficient energy transfer, the phase of the modes must match. When the phase is matched, coupling is strong. When the phase is mismatched, coupling becomes weak. Next is the spatial overlap. Coupling strength also depends on how much the modes overlap in space. If the modes overlap well, energy transfers efficiently. If they do not overlap, very little energy is transferred. Now, moving on to the methodology of the CM. First is the evanescence coupling. In evanescent coupling, light propagates inside the first fiber. A small portion of the light leaks outside as an evanescent field. When a second waveguide is placed nearby, the evanescent fields overlap, allowing energy to couple into the second waveguide. The last one is grating coupling. In grating coupling, a fiber is placed above a diffractive grating on a chip. Light from the fiber hits the grating grooves. The grooves scatter the light and provide additional momentum. This helps match the phase of the light, allowing it to couple smoothly into the waveguide. In summary, coupled mode theory explains how light transfers energy between modes by satisfying phase matching and spatial overlap conditions. Efficient coupling can be achieved using methods such as evanescent and grating coupling. Inside a waveguide, light can exist in multiple modes or paths. Light does not always travel in a single straight path. In optical waveguides, light follows specific patterns called modes, and it is known as the coupling of waves and modes. So, what is modes? Inside a waveguide, light can exist in multiple modes or paths. Each mode carries part of the light energy. When the waveguide is disturbed, such as by—
Have you ever wondered how light can jump from one path to another without even touching? This is where optical coupling comes in. Let's start with dual or multi-core optical fibers. Imagine several tiny highways for light, placed very close together inside a single fiber. As light travels through one core, a small part of its energy gently spills out, forming what we call an evanescent field. When a neighboring core is nearby, this energy can hop across, causing the light power to smoothly swing back and forth along the fiber. How strong this interaction is depends on how close the cores are, the wavelength of light, and the refractive index. Now, let's move to the chip scale with directional couplers. Here, two waveguides run side by side like parallel lanes. When light enters one guide, it quietly shares energy with the other through overlapping fields, creating a rhythmic exchange of power as the light moves forward. This simple yet powerful idea enables optical splitters, interferometers, and modern photonic circuits, proving that sometimes light works best when it shares the journey. Now, let's explore two more fascinating structures where optical coupling takes place. First up is the ring resonator coupling. Picture a tiny racetrack for light sitting right next to a straight waveguide. As light travels along the straight path, part of its evanescent field reaches the nearby ring. When the wavelength is just right, the light couples into the ring and begins to circulate, building up energy through resonance. Only selected wavelengths stay trapped in the ring, while the rest continues straight ahead, making ring resonators perfect for filtering and sensing applications. Next, we have photonic crystal waveguides. These are made from carefully arranged patterns of materials that control how light moves at the nanoscale. When two defect waveguides, or a waveguide and a cavity, are placed close together, their localized modes overlap. This allows energy to transfer between them with remarkable precision. Even tiny changes in geometry can strongly affect coupling, enabling slow light and ultra-compact photonic devices. Let's take a quick look at some recent advancements in photonic technology. First, we have photonic integrated circuits. Unlike traditional electronic chips that rely on electrons, these circuits use light to carry information. Lasers inject photons into the chip, where optical elements guide and control the signal, delivering higher speed, lower heat, and better energy efficiency in a compact design. Going even smaller, plasmonic and hybrid photonic coupling allow light to be squeezed into ultra-tiny spaces. By combining photonics for efficient transport and plasmonic for strong confinement, these systems enable fast, precise sensing and next-generation nanoscale devices.